This is the Chem 1 lesson, overheat and calculating heat with the temperature change. So first, let's kind of cover the difference between temperature and heat. In English class, I realized that those are kind of used interchangeably, but there are technically differences. Temperature has to do with the measurement of the movement of particles, so how fast are particles moving. The units are, typically you're going to see degrees Celsius, or you're going to see Kelvin in here. I realize on the news you see Fahrenheit. While heat is the energy, so it does have something to do with temperature, but it also contains potential energy. Then the units are joules. So heat is something that's transferred from one thing to another, while temperature is really just kind of taking a snapshot on how fast those particles are moving when you put a thermometer in something. So we've talked about phase diagrams, and we know that that has to do with what state of matter you have, right, or those phase changes as temperature and pressure change. But if we kept a constant pressure, because pretty much if you're in one room doing something, you're not probably changing the pressure very much. So let's say that we had normal pressure. So normal pressure, right, is 1 atmosphere. Let's say we're starting at a cold temperature and that we increase the temperature. So let's think about what's going to happen if you keep pressure the same, what's going to happen with the relationship between temperature and the heat energy in that substance. So first, right, we're over here, we're as a solid, we've got liquid, we've got gas. So first, we're just going to heat up that substance, and that temperature is going to change until we reach that first line. Once we reach that first line, that's a phase change, right? So solid to liquid, we know that what's happening there is melting. So as that substance melts, the temperature actually stalls, and it doesn't change. Once all that substance is then melted and we get to all those molecules being in the liquid state, the temperature is then going to go up until it reaches the gas state. And once it reaches gas, there's going to be another phase change, and that temperature is going to stall out. Now, that doesn't mean the heat energy is still changing, right? It's still gaining heat, but that heat energy is going to the phase change, whether that's melting or, in this case, boiling. Then once it's all turned into a gas, then the temperature would continue to increase. So you see this shape graph for most substance, where as heat is added, that substance is going to increase in temperature until it reaches that point where it's going to melt. Then it's going to melt. That temperature is going to stall out. Then once it's all melted, the temperature is then going to continue to go up again till it reaches that boiling temperature. Then it's going to vaporize or boil, and then we're going to heat up that gas. So you're going to see this staircase shape, this heating curve, throughout this, and how you calculate the heat involved has to do with where you are on the graph. Are we doing a phase change? Are we melting? Or maybe we're just heating up that liquid. You're going to use different parts of the graph. So first, let's go through and just answer some questions about this. So does the temperature increase during melting? So you're probably going to have to zone in here on that melting, right? We're right here. Well, is the temperature changing? Well, if you look, the y-axis does not change, so the temperature does not increase during melting. The heat energy changes, right? Is the energy required for the phase change? Yes, that's always required, right? That's our x-axis down here. Can both a liquid and gas exist at the same temperature? Yeah, it can. In this case, it would be at point D on our graph, right? We have both liquid and gas right here. And next question, what must be changed? Temperature, heat energy, or both during condensation? So first we've got to zone in on condensation. We've got that guy right here. So what's happening? Well, the heat energy is changing, but the temperature is not, right? That's a flat line. And last, how would you describe the change in arrangement of particles as heat energy and temperature increase? Well, those particles are going to start moving faster and become further apart. As they go from a solid, really closely tied together, not moving very much, to a liquid, moving a little bit more space between them, all the way to a gas, right, where they're flying around with lots of space in between them, expanding to fill their container. So as I've just described, is absorbing heat energy. So far we've talked about a heating curve as that substance is gaining heat energy. So this would be endothermic, right? Endothermic has to do with energy being absorbed by the substance, so the energy is going into the system. So endothermic on your heating curve would be going forward, right? It would be going from solid to liquid to gas. That means that that substance is absorbing heat energy, but the opposite can happen too. You can lose heat energy. That would be exothermic. That means that that heat energy is being released by the substance and going out into the environment. And that means we're actually taking this heating curve and going to the left, right? We're going the opposite direction. So sometimes you have to think about, well, is this substance gaining heat energy? That prefix endo means within, or is it losing heat energy? And that means it's exothermic, prefix exo meaning outside. So essentially, on a heating curve, there's two different things happening. So either you're dealing with a temperature change, right? Those would be our diagonal lines, or we're dealing with a phase change, and those would be our flat lines. So we actually have two different types of equations, whether we're talking about that yellow diagonal temperature change or the flat green phase change. So first we're going to talk about what to do when the temperature changes. So first we're going to be covering the yellow situation on the heating curve here. So in order to do that, we kind of have to talk about, in general, the substance's nature to absorb heat energy and change their temperature. So you go to the beach, you take your shoes off, you're real excited to be there, you put your feet in the sand, and the sand feels incredibly hot. Now most of you guys then choose to then run to the water, and how does the water feel? Nice and cold. So how come both of these things are absorbing the same heat energy from the sun, but the sand feels wicked hot, and that water feels at least a little bit cooler than that? That has to do with the nature of the substance. That's called specific heat. So specific heat is the measure of the capacity of a substance to absorb heat energy. And technically it's defined as the amount of energy needed to raise the temperature of 1 gram of something by 1 degree Celsius. So it's how many joules of energy have to go in to raise 1 gram of it 1 degree Celsius. So the units are a little long and weird. It's joules per gram degree Celsius. It's joules required to raise 1 gram 1 degree Celsius. And one good thing to keep in mind is something with a high specific heat can absorb a lot of heat energy without changing its temperature. It takes a lot of joules to change its temperature. That's a big idea here. So for example, you got two slides at the playground. You got a metal one and you got a plastic one. Well, the metal one feels incredibly hot. That's because it has a low specific heat. Its temperature goes way up with the addition of joules, while the plastic one's going to feel cool because it has a higher specific heat. It can absorb a lot of joules of energy before really changing its temperature. And the way I keep that straight is that water has a really high specific heat. So, man, that pot of water on the stove takes forever to get up to a boil because you have to put, that burner has to put a lot of joules of energy into it before the temperature is going to change. But the opposite is true too. Once you get that water boiling, it stays hot for a long time because it has to release a lot of joules of energy before the temperature goes down. So it works both ways. So back to the beach, that water feels colder because it has a high specific heat. So it means it can absorb a lot of joules of heat energy before its temperature is really going to change. It's the opposite of the sand. So that's kind of how you can keep those two ideas straight. So based on what we've talked about so far, we know that the amount of heat something contains depends on its specific heat, that nature of that substance, and the temperature change. So if you add 5 joules of heat energy to a substance that has a low specific heat, is the temperature going to change a lot or a little? Well, if that substance has a low specific heat, the temperature is going to change a lot, right? It's going to go way up. But if you added the same amount of heat energy to something with a high specific heat, the temperature is going to change only a little because it's going to take a lot of joules to change that temperature. But if I take that 5 joules of energy and I put it into 2 samples of water, so they have the same specific heat, the temperature change is going to be different. If I put it into a cup of water versus an entire pool of water, which one would change the temperature more? Well, that glass of water, that temperature is going to go way up more so than that pool. That pool is probably not going to change at all. And that's because the pool has more mass. There's more of it. So our heat calculation needs to include mass in it also. It depends on how, so sure, kind of the ability to gain heat and change temperature, how much the temperature changes, but also how much of it we have. So that completes our equation, where the heat involved in something, Q, is going to equal its mass in grams times C, that's our specific heat that nature to gain or lose heat energy, excuse me, temperature, so that joules per gram degree Celsius, and that triangle T, that is one variable, it stands for change in temperature. So that triangle stands for delta, it's a Greek symbol. Traditionally that's used in science classes to represent change in. So if it's delta T, it's change in temperature. So your units kind of all need to work out based on your specific heat, since specific heat has joules, grams, and degrees Celsius. Heat needs to be in joules, mass needs to be in grams, and change in temperature needs to be in degrees Celsius. To find the change in temperature, to find the change in anything really, it's final minus the initial. So if the temperature went from 80 degrees Celsius to 90 degrees Celsius, to find the change in temperature, you would take 90 minus 80, right? It changed by 10 degrees. So let's look at an example. How much heat is required to raise the temperature of a 50 milliliter sample of water from 25 to 85 degrees Celsius? So first let's think about our heating curve. So let's draw the same 5 steps we always are going to. There we go, diagonal, flat, diagonal. And if we're dealing with water, I know that this first flat line is going to be 0 degrees Celsius because I know water melts at 0 degrees. And our other phase change up there, boiling or vaporizing, I know that happens at 100 degrees. So if we're going from 25 to 85 degrees, we're kind of zoning in right there, right? In that middle diagonal line, I know water is only a liquid here. I know all of that joules of heat energy is going to go into changing that temperature. So I know the equation we're going to need to use. Q is going to equal mc delta T. And let's see, I'm trying to find heat, so we're trying to find Q, mass. Now, here's the catch. Mass needs to be in grams, and we don't have grams. We have volume. But since water is 1 gram equals 1 milliliter, I know that this equals 50 grams. So I do know my mass, 50 grams, times the specific heat. You will be given all these constants. You have a big table of them in your notes. It would be given to you on the test, not something you have to memorize. Now be mindful that you do have 3 for water. You have water as a solid, liquid, or gas. In this case, we're in the middle of our heating curve, so water is a liquid. So you're going to want to be sure you use 4.18 joules per gram degree Celsius times its change in temperature. In this case, it's going to be final minus initial, so it would be 85 degrees Celsius minus 25 degrees Celsius. So you're going to need to multiply those together. So first, I'm going to find that change in temperature. So 85 minus 25, that's really going to be, if you want to think about that, that's a 60 degrees Celsius change. So I've got to do 50 times 4.18 times 60 is going to give me a really big number. It's going to be, let's see, 12,540 joules. And I know that's the appropriate unit because the grams are going to cancel out here and my degrees Celsius are going to cancel out, so we're left with joules. So those units are going to help you with the algebra there on this. And sig figs, depending on your teacher, they might be okay with this answer. They may want you to round it to 3 sig figs. You're going to need to ask your teacher about that. So this last example is a little bit different. We're actually asked to find the mass. What mass of silver is present if it requires 225 joules of heat to increase the temperature from 13.5 to 45 degrees Celsius? So maybe the first thing you want to do is think about where we are on the heating curve here. So let's see, I've got the melting point, 962 on our first flat line, and then I have the boiling point up here on the second flat line. And if we are dealing with 13.5 to 45 degrees Celsius, we are way down here on our graph. So we're dealing with a solid and no phase changes because we're nowhere near 962 degrees, which is where this would melt, which is only shocking because it's silver that it has a really high melting point. So we know we need to use Q equals mc delta T. We're dealing with a temperature change here. And we're asked to find the mass of silver, so we actually have Q. We know that that's 225 joules. Is going to equal mass or unknown, I'm just going to leave it as an M, times specific heat. Now here we need to find the specific heat of silver. So you're going to need to look that up. So look at my giant list. Specific heat of silver is 0.233 joules per gram degree Celsius times its change in temperature. So in this case, final minus initial is going to be 45 degrees Celsius minus 13.5 degrees Celsius. So I'm going to go ahead and calculate that. 45 minus 13.5 is going to be 31.5 degrees Celsius is our change in temperature. So now that we've got our change in temperature, we now need to do the algebra to solve for M. Since m is what we're looking for, we're going to have to rearrange a little bit. So m is going to equal 225 joules divided by 0.233, our specific heat, joules per gram degree Celsius, times our change in temperature, 31.5 degrees Celsius. Now be mindful, depending on how you do type into your calculator, to use some parentheses. And you're going to get that mass equals 30.7. Now let's look at our units. The joules are going to cancel out, and the degrees Celsius cancel out, so we're left with grams, which is the appropriate unit for mass, so that tells us that we did the algebra correctly. So we don't always have to solve for heat. Sometimes we can solve for mass. You'll see that you can also solve for change in temperature, or even the specific heat if that's not given.